Hello and welcome everyone to this next session of the MZES Social Science Data Lab. My name is Dennis Cohen and I'm happy to welcome you all to today's second and final part of our Getting Started with Python workshop series by Ruben, Bach and Andreas Küpfer. The MZES Social Science Data Lab is an event series here at the Mannheim Center for European Social Research that provides a platform for presenting tools and methods for the collection, management, analysis, and visualization of data in the social sciences. In the current spring term, it is co-organized by myself, my colleague Andreas, and with the support of Andreas, who is our presenter here today. Given most of you here and online already met our speakers, one of whom is here today last week, they need no extensive introduction. Ruben Bach, who was our primary speaker last week, cannot be here today, unfortunately. So we're all the more grateful that Andreas, PhD student at the Technical University of Darmstadt, is here today to teach the second part of this workshop series. In the second part of Getting Started with Python, Andreas will introduce us to the applied use and some peculiarities of Python through a step-by-step tour of data wrangling, data visualization, and applied predictive machine learning with the scikit-learn package. Just a quick word on the logistics for today's talk. As usual, we are recording our session. We're recording in active speaker mode. What does that mean? It means for all of you here today in the room and everyone joining us online via Zoom, that your audio will be recorded. In case you're raising audio questions on Zoom and your camera's on, your video will be recorded as well. You can circumvent that by simply posting your questions in the Zoom chat or sending me a direct message, in which case I will read out the question for you. Okay, with that said, do feel free to ask questions at any point during today's workshop. And Andreas, once again, thank you so much for doing this today. The floor is yours.
Thank you, Dennis. So, let's start with day 2 of the Getting Started with Python workshop, a how-to guide for social scientists. And just for those who miss the session last week, I just want to give you a short recap, and we want to take a look at Google Colab, which we want to work today with. And for that, I just want to show you our schedule for today. So we start with the recap, then we take a look at the data set and methods we want to use today. And in the end, I would like to give you a short outlook what you can do with Python above that without scikit-learn, but maybe some more sophisticated models, for example, transformer models or computer vision stuff. So recap of day 1. What we did last week is looking more on the side, so how to set up everything. So for example, install Python, work with pip, work with conda, what kind of IDEs are there. And all started with why should you use Python and when you should use Python instead of R. And there were a few points there. And today we want to take a look especially on the state-of-the-art machine learning point, which is not deep learning today, but at least some machine learning, which you can do in R. But I think they are just more sophisticated and more evolved models and packages in Python, which you can use to do this. And so last week, we also took a look at Jupyter Notebooks. And why do I would like to show you Jupyter Notebooks this week also is because we want to use Google Colab. And basically, Google Colab is a platform from Google. This platform also uses Jupyter Notebooks, basically. And Jupyter Notebooks are, somehow similar to our Markdown notebooks. But they are web-based, so you open it in your browser and you can type code there and save everything. And there is some service running in the background. And you also can combine Markdown with code as you do in R Markdown. And there is much more stuff you can evolve, even HTML as you do in Markdown, and more packages. And install packages or look at packages can be done with pip. So the pip is the package manager we introduced last week, and you can check out all packages using pip list. And there are also magics, which provides other functionalities, but basically Jupyter Notebooks are, the other part for Python, as are Markdown notebooks. And this is just some preview. We will take a look at it on Google Colab later, what you can do in Jupyter Notebooks and how it looks like. So you can use Markdown. You have some output fields as you have in R Markdown, and we won't go deeper in this on the slides. What you see here is an output of a data frame as you know it from R, and there you can see some basic plots. There is the package matplotlib, which is quite famous. It's similar to ggplot, for example, in R, and you can plot your data, but it's not like there is not some kind of framework as it is for ggplot to create these plots. So it's the syntax is not the same, to say that, but we take a look at it on Google Colab. And as I talk about Google Colab, I just want to point out some important things for today. When you want to follow along the code, you don't really need a Google account because you can read code or view code on Google Colab without a Google account. But when you want to execute code and want to edit code, you need a Google account, so you need to log in. You can use 3 GPUs with Google Colab. We take a look at this, how it works, and how you can use them, and when you should probably use them, and when it's not necessary to have 3 GPUs or to have GPUs. And you can load data from Google Drive. You can even, as I did, export Google Colab notebooks directly to GitHub, to repo on GitHub, to connect both. And the downsides of Google Colab, you lose the data. So for example, when you do execute some code and you get some results, and then you close the Google Colab notebook and you log in later, everything will be gone. So you have to store it locally or store it on GitHub, for example. And I think these are the most important points to follow along today with the code and with Google Colab. And that's why I would like to talk more about the data set and the methods we intend to use today. And just to have some example, I used the wage data set of the population survey of 1985. It's some data set on OpenML, which is a huge platform with many different data sets, which you can also use to play around with Python and load the data. And it consists of more than 500 people and persons, and has 11 different features. All of them are numerical or categorical, which means there is no text involved. But basically, when working with text instead of numerical or categorical features in Python, it's as in R, it's just one more layer above. So you have to convert the text somehow to work with models in Python. But for today, we stick with numerical and categorical features. And the methods is, like, the first method is logistic regression, as you know it from R. And the second method is a random forest. The random forest is basically some decision tree, which is, like many decision trees combined with each other to get a random forest. That's basically the explanation, but you should definitely, when you want to use it in a project, read more about it. There is a lot of documentation available, for example, on scikit-learn, the package we will use today. But these are the two methods. This is the data set, and this is basically the pipeline we going to implement today, or we're going to take a look today. So first, we split the data. We use training data and hyperparameter optimization data, which is 80% of the full data set. And we evaluate everything on 20% of the data set. So this means that we won't do some inference today or something, but instead we aim for a prediction. So maybe you have a use case, you have a lot of data, and you cannot annotate this data set, but you annotate maybe 1,000 observations of the data set. And then you can train a model and do a prediction on the remaining unlabeled part of the data set. And this is what, like, basically these models in Python are used most of the time. So for the prediction case. And in the end, you can also do some feature importance. So you can, for example, show, okay, if you included 4 features in your models for prediction, you can see which feature has the most impact on the model decision. And yeah, that's basically the workflow for today and the data sets we use. And as I already mentioned, you need no local Python installation for today. So you can just use the Google Colab notebook, which will be make available via the chat on Zoom. And otherwise, for the people in the room, you can just go on the official GitHub repo of the Social Science Data Lab, and there you can see some link. I can show it also to you on the repo. Give me a second.
It's on the chat.
Okay, so it's also on the chat, but for the people in the room. So that's the repo, and down there on day 2, there is the code. And when you click on that, you have to wait a second. Then it loads, and you can click on a button opening Colab. And this is automatically generated when connecting Google Colab to your GitHub repo. And yeah, finally, you're in Google Colab Jupyter Notebook. And as you can see, you don't need any installation or something. You can start right now. I just want to give you some explanation about the overview and the interface of Google Colab. So on the left-hand side, you have some table of contents, as you know it from Markdown. So I'll show you how you do this, but you know, maybe with the hashtags, you can create chapters and sub-chapters, and it is displayed on the left-hand side. We can also close this here. And on the upper hand side, you have a lot of configuration opportunities. For example, you can choose a runtime and change the runtime type. And this is quite interesting for those of you who want to work with more sophisticated models, because then you often need GPU. For example, when you want to work with transformers or computer vision models, you need GPUs. And if you want to use a GPU environment, you can select it here. And it is basically free, but not available at every time. So for example, on peak times, sometimes Google Colab says, okay, it's not available right now. Then you have to wait. But yeah, most of the times, and especially when you want to try out something, but don't have GPUs right now available, you can use it. And again, GPUs are interesting for computer vision, for transformer models, so more sophisticated models, but maybe not random forests or logistic regression. So we don't need it today, but just that you know where to find it. So it's here, change runtime type. And I think for the other stuff, I don't really need to explain a lot, but maybe take a look at the code, so at the notebook itself. And what I want to do today is we want to load our data set into Python. So we load it directly from OpenML and look at the specifics. How's the data set about? What is the data set about? And second, we would like to apply a logistic regression model based on the machine learning library scikit-learn, which is quite famous and used in many cases. And third, we want to work with a random forest. And the last step will be just some conclusion, and I'll give you a look at how you could include ChatGPT if you can develop in R, how you could transform some R code into Python code just to have some learning assistant, maybe. Yeah, that's it. So maybe just to give you some idea how it works, when you do a double click on some code chunk, it opens some edit mode, and you can just do the formatting as you know it. So you can add hashtags and so on to create a title. On the right hand side, you have a live preview, how it looks like when it's rendered. And that's it basically, how you work in a text chunk. And you can create new text chunks with that button and add some text. And when you want to code, you have to create a code chunk, and you can start right away in your code chunk writing code, and you can execute the code clicking on this play button. And then it maybe takes a few seconds at the first time because it has to connect to the environment from Google. But then you can execute all the code you need. And for example, as we mentioned last week, but also before, you use pip to install packages. So in R, you would use install.packages, and then you write down the packages you want to install. In Python, actually use pip install or conda install, depending on the environment you use, but most of the cases, at least in Google Colab, we use pip. You need an exclamation mark before pip, and then you can install the packages, and you get some output, and in the end, usually the package is successfully installed. In that case, it was already installed by myself. And you can also install packages directly from GitHub, just adding some git plus and then the URL to GitHub, because in Python, a lot of packages are like, as in R also, but in Python even more, I think, developed on GitHub first. And there are some, especially for the state-of-the-art packages, the first release is always on GitHub, and you can install them from GitHub directly using the same command. And as we work in an environment already, which is Google Colab, there are a lot of packages already pre-installed. So there is no base Python in Google Colab, but already a lot of packages which are offered by Google or already installed by Google. And you can check these packages by using an exclamation mark with pip list. And as I explained, when I want to execute this code chunk, it takes a few seconds and hopefully gets executed, and you get the pip list. You can also try this on your laptops, actually. When you click on the link and work in Google Colab, you basically Google Colab creates a copy of the notebook on your Google account. So you can change anything. It won't affect my notebook. So, and it worked. And as you can see, you get a sorted list with all the packages, and there are already, also some quite famous packages installed, like TensorFlow, which is some machine learning package. And you always see the package name and the version on the right side. And when we scroll down, we also see, for example, what else? For example, RPy2, which what Ruben talked about last week, which is quite helpful sometimes to use some R functionality in Python. But anyway, if a package is not installed, you can for sure install it and use it in your environment. So these are the ways to install packages and to check which packages are already installed. But how Python works now. So I just want to take a brief look about the syntax of Python, base Python, so without packages. with one exception, NumPy, but basically NumPy is not base Python, but it's a very, very frequently used package to work with arrays and numbers in Python. So everything starts with import NumPy. What does import NumPy do? So basically it imports all the functionalities, all the modules of the NumPy package into your environment. And you can call these functionalities and modules via numpy.array. And this is a function. You give an array into the function. So an array is like a vector in R with some square bracket in the beginning and some square bracket in the end. And we create an array and we define a variable name. And you don't have these arrows like in R, but a simple equal sign. And in the end, we can use print, as you know it from R, and print our array. So this is basically your first line of code. And there are different methods to import these functionalities, these modules into Python. And we talked about that last week. But in the first case, we import NumPy as NumPy. So our package is called NumPy, and we always have to call NumPy dot some package, some functionality. In the second case, we say we do the same, but we want to rename NumPy because it's just some convention, I would say, that most of the people import NumPy as NP, and most of the people import pandas as PD. Pandas is another important package, like the tidyverse, parts of the tidyverse in Python. So when we go with import NumPy as NP, we can use np.array, and it's exactly the same, but we use a different naming for the package. The third case, and this is also quite interesting when you don't want to import all the functionalities of Python, but instead just one or two or three functions, for example, the array function, you use from NumPy import array, which means you don't have to write down NumPy or NP every time, but you can just use array and then define your array content. So 3 ways, and each way results in the same output. But you can decide which way you want to choose, which way fits for your purpose. We will see different ways in the next few code chunks.
You get some sort of error message if you load 2 packages. Let's just say it's NumPy and pandas, and they happen to name one function in the same way. Let's say the pandas package will also have an array function. Would you get an error message like an R, or?
Actually, I think it should be overwritten, like the last package you imported overwrites the package before. But I think you could avoid this quite easy. Actually, it makes sense to import the packages at the beginning of your script and all the functionalities, so you can, I think, avoid it. At least same names you can avoid by that. Okay. So we know how to import packages and functions, and in the next part we just want to write some basic functions. So it's like some custom function, and a function is defined with def and then a function name and then arguments. And the interesting part here is, and this is not only important for functions, but also, for example, for if clauses or loops, you have to use this indentation, and it always has to be the same in one notebook. So if you don't use it, there will be some error when we try to execute it. So always use the indentation. You can decide like how many spaces you put before the return, usually 2 spaces or one large space. And that's it basically. And then you use return without anything else, just a space, and you can even return not just one argument, one variable, but several variables. For example, in this case, we return 2 variables. And first our input item, and second input item plus pi. And pi is not just some variable which has to be defined, but it's a functionality from the math library, and it's also frequently used library, and it gives us back the pi value for pi, and we can call the function using our previously defined array and get back 2 variables, not just 1 but 2, and they are both defined, and when we print them, we see the output, and it worked as we would expect. And so this is how we define functions. And second thing, which is interesting in Python, when you use loops, there is one, I think, very Python specific type of defining a loop. And these are called inline loops. And you can define an inline loop by using a square bracket, or 2 square brackets, and in between you say, basically you use your array, you use an item, which is your iterator, and you use some method you want to call for each item in your array. So it says, do this functionality on each item in your array. And in the end, you get back your modified array. And this is called an inline loop, which is very fast compared to a normal loop where you would say for do, and then do a normal loop like you know it from Python and from R. And in the end, there are always different possibilities to achieve this. You can also say array.pi, and this basically adds pi on every element in the array. Yes?
Just a quick question, because that always confused me a lot about Python. So when you're talking about functionalities, like the array example, using a dot, that's specific to an element of that type, right? So if I have an array, I can only use NumPy functions on that object.
You mean like when I
the way you import it, I was trying to catch up, and then if you're using an array, which is an object from there's an array, so then I can only use functionalities from the NumPy package.
It depends. On an array, you usually would use functions from the NumPy package, but you can also easily convert an array to a base Python type, and then you can apply every other functionalities too. And like most of the times, also other functionalities are, let's say, adapted to the NumPy package, so you can also apply them on NumPy arrays. But it depends. Okay, so that's it basically, with just some Python code, some intro, how to import packages, how to write a loop, a function, a custom function, and that brings me to the first part of our use case, and that's, as always, loading data and exploring data. But before that, we actually have to install packages and import packages, because we don't intend to stick to the base package, to base Python, or to the installed packages from Google Colab, but we would like to check out other packages. For example, pandas. I already talked about it before, and pandas is a package to handle data frames, to data wrangling, data management, and there is actually a really cool explanation and documentation on the website. And you know that pip install pandas or conda install pandas, depending on the environment you use. And if you scroll down, there is even some documentation when you come from R, what functionality is offered in pandas and how you would do that in R. And I think this could be really helpful at least in the first weeks when working with Python and pandas, to have some dictionary actually. So I would highly recommend that to you, and just want to show that. Yeah, second package is matplotlib, and basically it's some data visualization package which goes hand in hand with the last package, Seaborn. Seaborn is more for sophisticated visualizations. Matplotlib is more for basic visualizations, some bar plots, some basic scatter plots, but we will take a look at it. And scikit-learn. So scikit-learn stands for scikit-learn, and scikit-learn is I think the most used basic machine learning library for Python. And you can do some classifications, some regression, clustering, dimensionality reduction, also pre-processing on the data. So a lot of stuff which is packaged in this library. And they have a really, really good documentation. They explain every parameter in detail. They have examples on their website. And also most of the tutorials you find out there about random forests or logistic regression or support vector machines in in Python, you will find with scikit-learn. So they most of the time use scikit-learn. So these are the 4 packages we need to install for today. And as we don't want to install all the packages all the time, we execute a code. There is a short routine, which I defined. And this routine just gets a package as an input, a package name, for example, pandas. And it checks, is a package already installed or not? And installs it when it's not there already. And you can also try it out to install the packages via this routine. And actually some packages may be also already installed by Google Colab, but it depends. And as we now got access to all the packages and installed them, we can use their functionality. And when working with some toy data and example data, it's sometimes quite useful to use scikit-learn, sklearn data sets, and they have some function where you can retrieve data from OpenML, and you can just put in the data ID of the data set, and then you get the data back. And in our case, as already mentioned, it's the wage data set, and the wage data set has some features, I think 11 features. And in the end, we try to predict the wage of a person. And how can we do this? So first, as always, we should take a look at our data set. And our data set, our explanatory variables are in wage survey X, and we can use the describe function on this data frame, and we can put some parameters in. Actually, we just want to show all the features and their like statistical informations, and then we get this nice overview about the features, as you know it from R, from similar functionalities there. And then we take a look at our target variable. So first, as you can see, we loaded everything from wages survey raw, which is basically our explanatory variables here. And second, we load everything from the target variable. So this is some kind of larger object where we can access different data within the object, and we can access the target variable, which is, by the way, explained on the functionality or on the scikit-learn website. We can access our target variable, our y, and we can use like wages survey raw.target.head to get the first 5 5 target variable values on this overview. And having this, we can do some basic visualization. For this, we just use matplotlib, which we installed before. And we can do a histogram by just access the target variable .plot.hist, and then we get some histogram. And we could add a lot of labels and colors and I don't know, but just to get some overview, this is quite helpful, I think, as you would do in R probably the same way. When we, for example, want to take a look at box plots, we can do this also by using matplotlib. So we import matplotlib.pyplot as PLT. So we rename the package to PLT and can define our box plot in a way it's shown here. So first we initialize the box plot. There's always a figure and an axis. We set some information on the axis, for example, the title. We also set the plot type as box plot. And we say we don't want to have any white ticks. So on that side. And in the end, we just say .show and we see our box plot. And that's how it works in matplotlib. And now, as we got some first overview, we want about the target variable. We also want to take a look at our explanatory variables, and this is really important when working with data frames in Python. So the first line here, line of code. Why did I put a copy there? It's because when I would not put a copy there, it would just point to the old data frame, but not create a real deep copy of the data frame. So when I would, for example, change that variable, for example, add a new column, also in the old data frame, wage server X, the new column would be added. And if you don't know that, it could be quite, time consuming to find this error. But this is interesting for Python, that you need this .copy in many cases. Maybe you want to create a copy of a data frame to do some deeper analysis on it, or for example, or some filtering. And in our case, I just want to insert the wage to our copy of the data frame so that I have all the information in one data frame and not in two different data frames. So I use insert, which is from pandas, and I say wage. This is the position in the column wise in the data frame, and the data I want to insert for the new column. And then I just want to check, okay, are there any outliers, for example, because as you can see there is definitely one outlier which has a quite high wage in the distribution. And I can do this by using ilog. Ilog is also an important function for data frames in Python to select rows by their index. And I can select the wage or the person with the highest wage by using our data frame, selecting the wage column, and then looking for the highest value in our data frame. And I get back the index, and then I can just print this here, and I see, okay, she's unmarried, she's female, and so on. So I get just this one object back. And I commented this out, but in case you would like to drop this outlier in the end, you can just use your data frame, put drop in the end, and put in the ID of the highest wage person, and it gets dropped. But I don't want to drop it for now. So let's continue with, and as already explained, with some more sophisticated visualization. So we don't want to have just some box plot or some histogram, but we would like to have some correlation plots. And this is done really easy with Seaborn. So this is the fourth package we installed earlier, and we import Seaborn as SNS, as you know, and we don't have to don't have to name it SNS. We can also name it, for example, C, but SNS is just quite common. And we again create a copy of our original data set and insert again our wage column just for the purpose of demonstration now. And then we can use a so-called pair plot with SNS. We put in our data frame, we say the kind, so we say regression, and then we get back this quite nice visualization where you can see all the relations between the different features in the data set. And yeah, this is just one example with one line of code, how you get quite nice plots in Python. I know, yeah, I also use quite often, like maybe most of the time, ggplot for my visualizations, but still in Python, it's also quite easy to create nice ones. And if you work already in Python with some data, why not use Seaborn or matplotlib, which is basically built on Seaborn on matplotlib to visualize the data. Okay, so I would just go briefly about, over this kind of section here, because it's just some simple bar plots of our features. What's interesting here is that I created some function in Python, again, some custom function. It's called distribution plot. It has 3 arguments, and there is some default value defined with none. And what this function does is you can give it a column name, a column label, and some labels for the ticks if you need it. And then it creates, bar plots for all the features. And that's just another example how you can use these custom functions in Python. And what we do next, which goes further into, let's say, pre-processing and checking what kind of data we have available in our data set. We want to check just the columns we want to focus on in our machine learning models later. So we would like to include sex, occupation, and merit in our machine learning models to keep it simple. But for that, we should take a look at whether there are NA values in our data set or not. And this can be achieved by using this command. So you use your data set with the features, which is already limited to our 3 features. Then you say, is NA values dot any? So are there any NA values in our data set? And then you get false or true back, and you can format some print, which makes it a little bit nicer in the output. And that's it basically to do this in Python. And that's the part now where we go into scikit-learn, so scikit-learn. And scikit-learn, as I explained earlier, is not only for machine learning models itself, but also the pre-processing of data sets before you want to apply some machine learning models. So that's why we also use it here for our pre-processing of the labels. And what we do here is scikit-learn has some functionality which is called label encoder. And what label encoder does is it changes features to labels which can be consumed by machine learning models in scikit-learn. And for example, occupation, as we can see here, is explained by different strings. And these strings are then converted to numbers just to have the categories organized in a better way for our model. And having this, we just need one more pre-processing step actually. And as I would like to do some binary classification in my machine learning models, it's quite unfortunate that we have continuous weight in our data set. So I just say, okay, people which earn below the mean wage are assigned 0, and for all other people, we assign a 1. And how is this done? In pandas, PD again, so import pandas as PD, there is a function which is called cut. And cut is really helpful when you want to apply binning. So quite often we would like to create bins for different groups of characteristics and data. And in our case, we use cut to create these two groups. So people below the mean of wage and people above mean of wage. And we can do this by, again, using these square brackets, as we used in our array before also. And we define ranges. So the first range is the range from 0 to the mean, so the target mean of our outcome variable. And the second range is the range from mean to the maximum value, which is, again, extracted by using .max. And we define the labels 0 and 1. And in the end, we have our outcome variable, which is basically looks like that. So we have just 0s and 1s in our data set, which is perfectly fine for the machine learning models. And we can use that within the models. And to give you an overview about the features we extracted before. So we used, like here, that we use the label encoding functionality. They look like that now. So we have 0 and 1 and just numbers and a data set. So things our models can work with. And the second, and probably for machine learning and also for like classification stuff in Python, most important, or one of the most important things is creating a train test split. So we always have to evaluate somehow how good our model is. And to do this, there is an scikit-learn function. It's called train test split. And it just splits on a random basis our data into 2 sets. So we have a train set and a test set. These are the features, x-train, x-test, and y-train and y-test are the outcome variables in the training set, which we use to train the model and optimize the hyperparameters of the models. The test set is for the evaluation. We can define a test size and so on, and many more parameters, but this is basically I would say, the default setting. How is it used most of the time? And the random state is like set seed, like seed in R, so that everyone else can get the same splits when he or she re-executes the code. So we now have our 2 sets, x-train, y-train, and x-test and y-test. And we first want to apply the logistic regression model. But this is somehow different compared to R, because again, we want to train the model on data, on our data with the 3 features, and we want to use it for prediction. Usually you would use such a model, for example, if you have tweets and you want to classify these tweets somehow, you would annotate a random sample of tweets, and then you would train this model on the annotated sample of tweets, evaluate it on some out of sample data, and then you could predict on an unlabeled set of tweets. But in our case, we use this toy data set to demonstrate how the method works in Python. So we use scikit-learn linear model. So you can see this as a, let's say, like a tree. Yeah, so you have first scikit-learn, then there's linear model, then there are other types of models, and you go through you navigate through the big package, getting smaller. So you go scikit-learn, linear model, and from linear model, you have still a lot of different functionalities, and we just want to use the logistic regression functionality. And we want to import also metrics, because we want to evaluate our model. And we focus on the F1 score, which is, yeah, actually the most important metric probably. Another metric which we would also report usually is precision and recall, and maybe also accuracy, but F1 score is what we focus on right now. To initialize our model, our logistic regression, we just call this this function there, put in a random state, and write the model back to CLF. CLF is just a variable which stands for classifier. And then we do the fit on X train and Y train. So we train the model on our train data and predict on the test data with CLF.predict. And these predictions we can compare. So Y-pred we can compare with Y-test. And Y-test would be, in a real case, our annotated sample. And then we can also decide how we would like to average our F1 score if we have a lot of categories. In our case, I say just weighted, and we can print out the F1 score. The F1 score goes from 0 to 1. In our case, it's 0.61. And we did not tune any parameters. What does this mean? Actually, these models have a lot of so-called hyperparameters. And these hyperparameters, if you don't tune them, in a lot of cases, we suffer from bad performance, because these hyperparameters are important to boost the model's performance. And so we should tune them. And we can take a look at the hyperparameters of logistic regression. When we go to getParams.keys, then we get all the hyperparameters. Not all of them are really important to tune, but at least some of them you should definitely care, and you should tune the hyperparameter values when you train it. And so you go in the next step to, again, with NumPy, you create some values, some possible values for these hyperparameters. So you say, what could be a value for such a hyperparameter? And you define a range. And I just define in a log space using NP, using NumPy, a range of values for hyperparameter C, which is this range, I think 50 or something around that. And I define a value, possible values for class weight and possible values for sulfur. Just 3 hyperparameters to play around with. And then I get a param grid. So I get, basically, I try to put in all the possible combinations of parameters for the model when I train it. And as we have to try out all the possible combinations of hyperparameters now, we can again use scikit-learn. Randomized search CV is again a function of scikit-learn, which tries out not all, but in a randomized way, some combinations of parameters. So we put in the logistic regression model, which we defined before, our param grid, how many iterations the model, the randomized search should try out, and use cross-validation, which is another method of machine learning. And then we say grid.fit. Again, we use our X train and Y train. And in the end, we just print out the results. So the best hyperparameters on our logistic regression model are Solver LBFGS, class weight none, and C6. And then we can use these best hyperparameters to fit again a logistic regression model and calculate an F1 score. And in that case, the F1 score is actually the same. So there is no real improvement by tuning the hyperparameters, which could be in some cases, but this does not mean that you should not tune them, because when we take a look at the random forest, it's the same procedure as for the logistic regression. So we just use random,
I assume F1 score higher is better.
Yes, F1, yeah.
Is there like a convention of when you should accept a model?
It's difficult. It's not that easy that you can say F1 score of 0.8 is perfect. You cannot say that. You have to compare. Like usually you would go the way to say, I use a logistic regression, a random forest, and maybe a support vector machine. You compare these values and probably go with the best model, but then you still have to somehow check, what are the weaknesses of the model. So you cannot say 0.8 is good F1 score or 0.6 is a good F1 score. But you can compare with other models, for example, also with random baselines, just to have some weak baseline to see whether the model is able to learn something or not. Yeah. So the second model, as I just explained, it's quite similar. You just use the random forest classifier. Maybe you mentioned, you've seen it already. It's not from point linear underscore models, but from ensemble models. So it's some kind of different model group, but there is no difference in the code actually. So we again initialize the model, do a fit on a model, predict on a model, and we get a F1 score without tuning hyperparameters, and the F1 score is 0.67. So it's without tuning better than our logistic regression model. As we again want to tune our values, I select some hyperparameters from random forest. I define value ranges using random from the random package, and I also need pandas somewhere. Actually, I don't need it, but I used to need it. But so you don't need it there, but you need random definitely. And then you get the random the param grid with the parameter combinations. You again do a randomized search CV using scikit-learn and using the same parameters except the random forest classifier. And when we do the fit, it tries out a proportion of the parameter combinations and prints out the best parameters, like according to your training set or to your evaluation set, which is created within. And then we use this model to predict. And as you can see here, we get a considerably better F1 score. So it's 0.73 compared to 0.67. So that just shows us we should definitely try to tune our models and not just use some values we think they are good, but we should tune them. And for that case, Python is a really, really good way to do this because, as you can see, it's quite easy. You just need, I don't know, 20 lines of code to train and tune a model and to evaluate it in the end. And the question now is how did the model decide that some observation is classified as 0 and some observation is classified as 1? And to get some idea on what the decision of the model is based on, there is some way to extract feature importances. And these importances are already included in scikit-learn in your model. So as you can see, results is created here. with our fit, so our randomized search CV, and within this results variable, you can access the best estimator. So we have a lot of estimators because all combinations of the model are tried out, and you can extract the feature importances from this best estimator. And this is what the model says. So how the model decides which person belongs to which category. And occupation has an importance of 0.78, which is quite a lot compared to sex or marriage. And for sure, this is just some example, and you have to include many more features, definitely, or other features probably, and use other models, try out other models. But I think it's also important to check this out just to understand the decisions of the model and not just the F1 score. Yeah, that's basically what I wanted to cover in terms of code with you. Just to show you how you could import a package, how you work with scikit-learn. When you would like to work with text data, it's, as I already explained, it's not really more sophisticated. There are also quite easy functions in scikit-learn available for you to do the pre-processing, which is needed to work with text data. But then it's basically the same. And in the end, or maybe in between, are there any questions regarding scikit-learn or the models or the package imports? Okay. Then I would just talk briefly about, if you want to learn Python, how could you make it easy for yourself? Like, there are different ways. There are a lot of tutorials. There's a lot of stuff you could cover and work on. But actually, I think if you can program in R, you can use ChatGPT to actually translate code, basic code, not sophisticated code, but basic code from R to Python. And this works quite good, actually. And there is also explanation for each line of code and in the end again. And also if you, usually when you, stuck at some error in your code, you Google it. But you can also, when it's not some sophisticated code, some complicated code, you can also use ChatGPT to ask it, and sometimes it helps, sometimes it does not help. You always have to evaluate, definitely, but just to have some learning assistant with you, which helps you sometimes, it could be interesting, especially especially to explore some specifics of Python. For example, the one below with inline loops. I think ChatGPT can help you in some ways. And there are just some examples, and with that I would like to conclude. Maybe just one more thing, some guidance how to survive in scikit-learn, probably, because there are so many estimators and stuff you could apply on your data. And I just added you some guidance on choosing the right estimator using scikit-learn. Definitely, there are also other packages you can apply, but scikit-learn, is the most famous. And it's just some tree or some brainstorming map, maybe. There is some start. You can see, okay, do I have more than 50 samples? Samples means observations. If no, okay, get more data. If yes, you can just go through the tree and add some estimator. For example, I end at linear SVC, then I click on that, and then I get the explanation what's a support vector machine, for example, and also code implementations. And that's one thing I wanted to mention. Then there is cheat sheet, as you know it from R. There are also cheat sheets for pandas for sure, for NumPy and so on. And there is also a lot of stuff beyond scikit-learn, because I think some functionalities of scikit-learn are also implemented in R. I know that, and that's why Python gets really interesting when you take a look at deep learning, when you take a look at transformer models, at computer vision stuff, and then probably TensorFlow or PyTorch become more interesting for you. And they also have a lot of tutorials and YouTube series on their website, which I highly recommend to you when you want to take a look at this kind of models. Yeah. With that, I think I would conclude, and thank you very much. If there are any questions, feel free to reach out.
Maybe any questions online? Maybe I have a question for you. So just since you showed us that, so you made this example, right, that we have the scikit-learn package, then we have the class of linear regression or the class of metrics, and within those we have different functionalities.
Mm-hmm.
How would we proceed if we wanted to know the big picture and see what functionalities we have available as part of a broader package?
It depends. I would say, for example, for scikit-learn, I would just check out the documentation. You have kind of the documentation is kind of a hierarchical building of these not dependencies, of the functionalities of the package. Otherwise, depending on your IDE, you can also go there and think it does not work in Google Colab, but in other IDEs, as we talked last week about, for example, PyCharm, you can also check out by typing just the first letters, then dot, and then you get all the available functionalities. I think that's the most easy part to get these. But there is no, I don't think that there is a real overview of all inner modules of a package.
We have another question online, namely about the naming of variables and commands, and what's the logic to using dots as opposed to underscores?
Actually, these dots are not the naming of the variable, but the dots are used when calling a function of an object. So I say, for example, here I say grid is randomized search CV. So I assign an object of randomized search CV to the variable grid, and grid includes other functionalities, other functions which I can call with grid.fit. So fit is a function within grid. So it's not the naming of the variable. I think I'm not sure whether you can name a variable with dot. I think it is possible, but usually I would go with underscore or hyphen.
And maybe just to follow up on that. So in this example, where you're printing the best parameters from grid, best params with a trailing underscore, that's just a part of the object, right?
Yes. Yeah. So that's just the name of the variable within the grid object. Yeah. And there are a lot of different available variables within grid. Yeah.
What would we do if we wanted to know what variables we have in that grid object?
Actually, think I cannot print it right now because I don't have to execute it. I didn't execute everything, but usually you can just print out grid, and then you at least somehow, not every time, but most of the time you see the object and also some contents of this object. But this depends on the package. Yeah.
But is there like an equivalent to the structure str command in R?
I think there is one, yeah, actually, but I don't have it in mind right now. Usually I just go there and I use my IDE and say grid dot, and then I see what kind of variables are available attached to the object. Yeah.
So just using autocomplete.
Yes, autocomplete. Yeah.
Any more questions? Seems we also don't have any online. So first off, let's thank Andreas for this workshop. Thank you all here in the room today and you joining us online for being here. Just a quick heads up about our next events. We will be back in 2 weeks from today, same time, same place, with a talk by Zaza Zindel from Bielefeld University, who will talk about social media ads for web survey participant recruitment. So thank you very much. We hope to see you in 2 weeks. Bye-bye. Have a nice day.